So this is the first lecture in the Organic Chemistry lecture series. Today we're going to be focusing on Chemistry 112, Chapter 1, which focuses on chemical structure and bonding. This chapter is going to contain a fair amount of review from General Chemistry 1 and 2, and will then apply concepts from general chemistry to new concepts that are relevant to organic chemistry. As an introduction, let's talk a little bit about the field of organic chemistry. So, why is organic chemistry a very important field of study? Well, one of the more compelling reasons is that living things are composed of organic molecules. We have alanine, for example, which is an amino acid. We have glucose, which is an example of a sugar, and cholesterol, which is an example of a steroid. Understanding organic chemistry and the principles of organic chemistry allow us to understand organic structures and understand the function of organic molecules, most importantly in biological systems. Organic compounds are often the principal active components of medicines. And as a species, humans have been consuming, isolating, and interacting with organic compounds throughout our history. We would, for example, extract aspirin from bark. Some people would literally take the bark and chew on it in order to ingest the aspirin contained within the bark. Penicillin is another classic example, which was isolated from biological systems. And sulfonylamides represent a broad class of antiviral drugs that are even used today in some form or another. In early times, it was thought that organic compounds could not be synthesized in the laboratory as they contained a, quote, vital force because they were from living sources. One of the really important studies early in the field of organic chemistry was in 1828, where Wohler showed that it was possible to convert an inorganic salt of ammonium cyanide into an organic substance known as urea. And really, throughout history, chemists have sought to prepare organic compounds in a defined and controlled manner. So, what is the field of organic chemistry? Organic chemistry is the study of carbon compounds. Many, many compounds contain carbon, and carbon is really a versatile element in that it is capable of forming four bonds with a unique three-dimensional shape. And this connection between structure, shape, and function is really critical, especially in the context of biological systems. So, what will you learn from studying organic chemistry? You will learn how to predict the physical and chemical properties of organic compounds. You'll be able to look at the structure, for example, of acetic acid and predict a property such as acidity. Noting acetic acid in this case has a pK of around 4.7. You will learn how to characterize and identify organic compounds. You'll be able to go from a collected proton NMR spectra or other spectra, and in turn deduce the structure of an organic compound. Finally, you'll learn how to predict the products and outcome of organic reactions, and you'll learn how to analyze and synthesize organic compounds. So, for example, you'll be able to propose a reasonable synthesis of, for example, aspirin from a known defined starting material. So, by studying and understanding these various organic reactions, we can begin to apply these reactions to prepare compounds with a defined structure and a defined function. Really powerful stuff. So, as our starting point, let's start at the most fundamental particles, the most fundamental components of structure, which are electrons and valence electrons. We're going to rely heavily on the periodic table. in order to go about calculating and identifying the subatomic particles found in a given atom. So atoms have protons, which are positively charged particles, and electrons, which are negatively charged particles. The number of protons and electrons in a neutral atom is equal to the atomic number, which is given the symbol Z. You can determine the atomic number Z from the atomic symbol and the periodic table. So for example, if we look at chlorine, we see that the number above the atomic symbol is our atomic number. This atomic number for chlorine is 17. Thus, if we're asked the question, how many electrons does chlorine have? It has electrons equal to its atomic number, which would be 17 electrons. This is true for neutral chlorine. We're going to have to account for the fact that we can be dealing with ions in some cases. And for charged particles, such as cations, which are positively charged, and anions, which are negatively charged, the number of electrons is equal to the atomic number minus the charge. So for example, for sulfur, if we go to find sulfur in the periodic table, sulfur has an atomic number of 16. So then, if we wanted to calculate the number of electrons, we'd take our atomic number, which is 16, minus the charge. Since this is sulfur 2 minus, we have a charge of -2, and that gives us, for our number of electrons, 18. You're going to see this number a fair amount, mostly because when we look at ions, their electron counts will often be that of a noble gas. We'll talk about that more in a moment. Looking at potassium, potassium has an atomic number in the periodic table of 19. So then for potassium, the number of electrons in this case is equal to our atomic number, which is 19, minus the charge. In this case, because we have potassium plus, in other words, potassium plus 1, for our number of electrons, we have 18 electrons to work with. With these representative examples in mind, I'd like you to take a moment here and work through the following examples, and I'd like you to tell me how many electrons do the following atoms or ions have. So I would encourage you to pause the video at this time, and we'll go over these examples momentarily. So looking at nitrogen now, nitrogen has an atomic number of 7 based on the periodic table, so neutral nitrogen would have 7 electrons. O2 minus, oxygen has an atomic number of 8. For our number of electrons, we take our atomic number minus the charge, which is -2. That gives us an electron count of 10. For carbon plus, this is a bit unusual, but it's important to know how to calculate the number of electrons for even somewhat unusual ions, as this will serve you well later on. Carbon has an atomic number of 6. For our number of electrons, we take our atomic number minus the charge. In this case, the charge is +1. So that gives us an electron count of 6 minus 1, which is 5 electrons. Now, although the overall electron count is helpful from the perspective of structure and bonding, valence electrons are by far the most important electrons. Valence electrons are the outermost, highest energy electrons. And valence electrons are used for bonding or lost during ionization, depending on whether we're forming a covalent or ionic compound, respectively. We can calculate the number of valence electrons by looking at the group number for a given element. So for example, if we're trying to identify how many valence electrons does hydrogen have, if we look at the periodic table, the number and letter above each column in the periodic table indicates the group number, which in turn indicates for hydrogen, hydrogen has 1 valence electron. We can also deduce that from the fact that looking at its outermost electrons, it just has one outermost valence electron. But that method is we're going to have to talk about in a little bit more detail later on. If we're trying to identify, for example, how many valence electrons does carbon have, let's take a look at carbon now. If we look up and identify the group number, in this case, our group number is equal to 4. So then carbon would have 4 valence electrons. Okay, let's see how we can apply this further. It's now time to talk about how we describe electrons, specifically how we describe electrons using what we call orbitals. So electrons are small subatomic particles with both wave and particle properties. And we can model electrons using orbitals. Now, what is an orbital? An orbital describes the region of space an electron with a given energy is likely to be found. This has to do with the fact that due to the uncertainty principle, we cannot exactly know an electron's energy and position with absolute precision. The way I like to think of orbitals is like a cloud of electron density, and it represents the general region of space where electron density is likely to be found. Here are some examples of various orbital types, the s, p, d, and f orbitals, respectively. And we can describe these orbitals using a series of what are known as quantum numbers. So let's talk about these quantum numbers as they do tie into the periodic table. So n, the principal quantum number, is the first quantum number. And when we talk about describing unique electrons, each unique electron and each unique orbital for that matter has a unique set of quantum numbers, n, l, ml, and ms, respectively. N, the principal quantum number, dictates orbital size and energy. So n counts in whole numbers 1, 2, 3, 4, etc. So it counts in increasing increments of 1. As n increases, the orbital size, electron energy, and distance from the nucleus increases. So if we look at, for example, an n equals 1 or a 1s orbital, you see that the 1s orbital is much smaller than the 2s orbital. Why is this important? Well, if we have the nucleus sitting in the center of our atom and we compare the distance of the electron from the nucleus, when we look at a larger orbital with a larger principal quantum number, this electron is in general farther from the nucleus. And this in turn implies it is higher energy. Now, each unique n value corresponds to a unique shell. What is the periodic table interpretation of this? A shell is a row in the periodic table where the principal quantum number corresponds to the row number. So for example, the first row in the periodic table would be the n equals 1 shell. The second row would be the n equals 2 shell. All orbitals with the same principal quantum number are in the same shell. Here's where things get interesting. Each shell is divided into subshells based on their angular momentum quantum number, or L value. So as we can see in the second row, the second shell, we have two distinct subshells. For example, the subshell on the left is the S subshell. The subshell on the right is the P subshell. So how do we make sense of this? Well, To make sense of these subshells, we're going to have to look at L, which is the angular momentum quantum number. The angular momentum quantum number specifies orbital shape, where L counts from 0 all the way to n minus 1. So depending on your principal quantum number n, a certain set of L values are permitted. So for example, if we look at various L values, L equals 0 corresponds to the s orbital, which has this distinct spherical shape. L equals 1 corresponds to the p orbital, which has this almost dumbbell or barbell shape. L equals 2 corresponds to the d orbitals, and L equals 3 corresponds to the f orbitals. A subshell in the periodic table interpretation is a unique section of the periodic table with a unique L value. So as we saw in our prior example, we have the S and P subshells in the periodic table. And as you get further down in the periodic table, you begin to see more unique subshells. Let's talk now about the magnetic quantum number. ML, the magnetic quantum number, specifies orbital orientation, and ML varies from negative L to 0 to positive L. So ML depends on the angular momentum quantum number. The number of unique orbitals in a subshell is equal to the number of unique ML values. So let's do a study of the different orbitals and take a note both on their shape and the number of orbitals. So starting with the s orbitals, these correspond to L equals 0. They're spherical shaped, and as such, there is one orbital orientation. So if we look at the s subshell, there's one possible orbital orientation. When we look at the p orbitals, these correspond to L equals 1. These are dumbbell shaped, and there are 3 different spatial orientations, and as such, there are 3 unique orbitals, corresponding to ML values of 1, 0, and minus 1. We call these p orbitals px, py, and pz respectively, based on what axis they're oriented upon. So as you can see, as L increases, we have more possible orbital orientations, and as such, we have more unique orbitals in a subshell. This is going to help explain why each subshell has a different maximum electron occupancy. Now, there's one thing I need to draw your attention to, as it's going to be very important in the context of looking at organic structures later on. And this is the idea of nodes. As you notice, the p orbitals contain what is known as a node. A node is a region of space that has 0 electron density. The number of nodes correspond to n minus L minus 1. Now, why is this relevant? Well, as we'll see later on, the number of nodes can have an impact on the orbital energy. The last thing I want to draw your attention to regarding the p orbitals concerns how they are drawn. When we draw a p orbital, one thing I'd like you to note is that the p orbitals are phased. We will unpack this concept later on in the lecture, but I'd like you to get in the habit when you draw a p orbital to draw the p orbital with one lobe shaded and the other lobe unshaded to represent the phasing of p orbitals. We'll talk about why that's important later on in this lecture. So, When we think a little bit about how to represent and how to describe electrons, we often rely on what are known as orbital box diagrams. We've done a reasonable job so far of establishing the different types of orbitals. Let's now talk about how we describe the electrons in those orbitals. So ms corresponds to the spin quantum number, which specifies electron spin. This can be either plus 1/2 or minus 1/2. Now, what is electron spin? Well, it is the direction of the electron's magnetic moment. So electrons generate a small magnetic field, almost as if a charge was spinning. The electrons are not actually spinning in place. The electrons just generate a magnetic field that's unique for that electron. Now, opposite spins pair in a given orbital. So if we have a given orbital that we represent by a box, we can have 2 electrons per orbital. These electrons consist of one quote-unquote up spin with an ms of plus 1/2 and one down spin with an ms of minus 1/2. ms is used to describe a specific electron in an orbital. And because there are 2 possible ms values for an electron, each orbital can hold a maximum of 2 electrons of opposite spins. Key takeaway here, maximum of 2 electrons per orbital. Very important. So we can use what we've learned from these various quantum numbers and begin to prepare what are known as orbital box diagrams. And to guide our construction of these orbital box diagrams, we have to follow what's known as the Pauli exclusion principle. Each unique electron one moment. So we're going to follow what's known as the Pauli exclusion principle, where each electron has a unique set of quantum numbers. In other words, each orbital can hold a maximum of 2 electrons. We're next going to talk a little bit about how our shells sorted by energy. Generally, as n and l increase, orbital energy increases. We're going to follow this general filling order, which should be review from general chemistry. Now, as we have now sorted our orbitals in terms of energy, we're going to now fill these orbitals from the lowest to highest energy. So electrons will occupy the lowest energy orbitals first, and then higher energy orbitals are filled afterwards. Orbitals of the same n and l value have the same energy and in turn are filled with equal preference. There's one last rule to consider, which is known as Hund's rule, which states that you will pair electrons only after empty orbitals of the same energy are filled. So let's go about creating an orbital box diagram for carbon. So I've taken the liberty of pasting in a figure containing each of the orbitals sorted in terms of energy. Let's now take a look at carbon and let's make an orbital box diagram for carbon. So for carbon, first and foremost, we need an electron count. Carbon has an atomic number of 6, and as such, it has 6 electrons. We're going to take those 6 electrons and use that to fill our orbitals from the lowest to highest energy. So we're going to start with the 1s orbital, which has one box, one orbital, and can accommodate 2 electrons. So we're going to place our 2 electrons, one up spin, one down spin. That in turn gives us 4 electrons remaining. We place our next 2 electrons in the next highest energy orbital, which is the 2s orbital, which can also hold 2 electrons. We have 2 electrons remaining, and those 2 electrons are placed into the 2p orbitals. Because these orbitals are of equal energy, we call this degenerate orbitals. We fill these orbitals with equal preference. Now, you may be tempted to place that second electron in the same 2p orbital, but following Hund's rule, we pair electrons only after empty orbitals of the same energy are filled. So we're going to place our second electron as an upspin electron in another 2p orbital. We can, in turn, summarize this orbital box diagram as an electron configuration, which would be 1s2, 2s2, 2p2. So there are many ways to describe the electrons and valence electrons that carbon has. Orbital box diagrams are one way of describing the energy and general position of electrons found for a given atom. These orbital box diagrams are really helpful because they allow us to more effectively understand the valence electrons and how those valence electrons can engage in bonding. Okay, so in terms of writing electron configurations can be thought of as a summarized version of an orbital box diagram. For electron configurations, you'll count electrons and fill in the orbital box diagram. Once you have your orbital box diagram prepared, you can count the total number of electrons in a given orbital and an L value, for example, the 2s and 2p orbitals. You will then list the subshells in order of energy that contain electrons and indicate the number of electrons in that subshell with a superscript, for example, 2s2. When you're trying to identify the valence electrons are electrons in the outermost shells, so they have the largest N value. Just to note, remember our maximum electron counts. The s subshell has 1 orbital and can hold a maximum of 2 electrons in that orbital. The p subshell contains 3 unique orbitals, and those orbitals can hold 6 electrons total. So let's do an example. We're going to write the electron configuration for nitrogen, and then we're going to circle the valence electrons. So, going to the periodic table for nitrogen, nitrogen has an atomic number of 7. So we have 7 electrons to work with. I'm going to make a basic orbital box diagram. So we have the 1s, 2s, and 2p orbitals arranged in order of increasing energy. Notice for the s subshells, we have 1 orbital. For the p subshells, we have 3 orbitals. From here now, we're going to fill this diagram with our electrons. So let's do just that. We place 2 electrons in the 1s, 2 electrons in the 2s. We've used up 4 electrons. We have 3 electrons remaining. Those 3 electrons go into the 2p orbitals. Remember, following Hund's rule, we pair electrons only at the end. From here, we can write our electron configuration, noting in our 1s orbital, we have 2 electrons. In the 2s orbital, we have 2 electrons. And in the 2p orbitals, we have 1, 2, 3 electrons. Identifying the valence electrons, these are the electrons with the largest N value. That would be N equals 2. And this tells us that we have 5 valence electrons. Given that nitrogen is a 5a element, everything checks out. Okay, So now that you've seen this representative example, let's apply what we've learned. And I'd like you to generate and write an electron configuration for oxygen and circle the valence electrons. So you may want to pause the video at this time and work through this example. Okay, so looking at oxygen, oxygen has an atomic number of 8, so we have 8 electrons to work with. I'm going to generate my orbital box diagram, and now we're going to fill this orbital box diagram with our 8 electrons. 1, 2, 3, 4, 5, 6, 7, and we have to pair electrons. Remember, you completely fill a subshell before you move on to the next highest energy shell or subshell. From here, we count in our 1s orbital, we have 2 electrons. The 2s orbital has 2 electrons, and the 2p orbitals have 4 electrons. Identifying the valence electrons as the electrons in the outermost orbitals with the largest principal quantum number, we see that for oxygen we have 6 valence electrons, and that matches the fact that oxygen is a 6a element. Always important to make sure that your final answer makes intuitive sense. Okay, so from these examples, we're starting to notice a bit of a trend. Because atoms often use their highest energy outermost valence electrons and valence orbitals to form bonds, we're very interested in the valence electrons. And as we've seen, main group elements have valence electrons equal to their group number. So this isn't just an arbitrary rule. We've demonstrated this rule through these examples. And if you did more examples looking at the electron configurations of other elements, you'd arrive at this conclusion. Now, let's talk now about Lewis dot structures and Lewis dot notation, which is our first foray into drawing reasonable structures for organic compounds and compounds in general. So we can abbreviate the valence electrons in Lewis dot structures using dots to represent electrons. One dot is one valence electron. So for example, lithium is a 1a element, would have one dot. Beryllium, 2a, 2 dots. Boron, 3a, 3 dots. Carbon, 4a, 4 dots, and so on and so forth. Let's apply this idea and let's do an example. Let's look at the Lewis dot structure for sulfur. Sulfur is a 6a element, so it has 6 valence electrons to its name. So we would draw 6 dots around sulfur. Now that you've seen this representative example, I'd encourage you to pause the video at this time and try drawing a Lewis dot structure for chlorine. So taking a look at chlorine, chlorine is a 7a element with 7 valence electrons. Looking at chlorine then, as it has 7 valence electrons, we would draw 7 dots. And this gives us a complete Lewis dot structure for chlorine. Now, how can we use these Lewis structures and interpret Lewis structures? First, let's talk a little bit about the idea of bonding electrons, and lone pair electrons. So atoms can share electrons, and the reason why they prefer to share electrons is that electrons in bonds are more stable than electrons in isolated atoms. This makes sense intuitively because if you can place your negatively charged electrons in the proximity of 2 nuclei, those electrons are stabilized by both nuclei. Atoms generally will share electrons to form what's known as an octet, 8 valence electrons in total. Hydrogen prefers to form 2 electrons. You can call the octet rule the noble gas configuration rule, as that's also really what's happening. Bonding electrons are shared in pairs between atoms participating in a covalent bond, and these bonding electrons are counted as belonging to both atoms in a bond. For example, looking at this hydrogen-hydrogen bond, these hydrogens are sharing a pair of electrons, and as a result, if we look at each hydrogen atom individually, this hydrogen atom is considered as having two valence electrons, while the other hydrogen atom is also considered as having two electrons to its name. As you can see, by bonding and sharing electrons, each hydrogen is able to achieve a noble gas-like configuration. So hydrogen has two valence electrons to its name, and this 1s2 configuration is comparable to that of helium. In general, these kinds of noble gas configurations are especially stable. This is why atoms will often prefer to form bonds to achieve a noble gas-like configuration. Okay, so in addition to bonding electrons, we have to consider what are known as lone pair electrons. Lone pair electrons or non-bonding electrons are electrons that are not shared between atoms. Lone pair electrons are counted as belonging only to the atom containing the lone pair. So for example, if we look at chlorine, the Lewis dot structure for chlorine looks something like this. Here we have a combination of bonding electrons and lone pair or non-bonding electrons. So let's do a quick electron count. So in this case, starting with the chlorine atom on the right, we have two bonding electrons that are counted as belonging to both chlorine atoms. And this individual chlorine atom has 1, 2, 3, 4, 5, 6 lone pair electrons. In total, this chlorine atom has 8 electrons to its name and thus fulfills the octet rule. The chlorine atom on the left also has 2 electrons from the covalent bond plus 2, 4, 6 non-bonding lone pair electrons, giving us 8 electrons in total. As you can see, each of the chlorine atoms has a complete octet or a noble gas-like configuration. Looking at hydrochloric acid here, we can apply the same analysis. In this case, starting with hydrogen, hydrogen has 2 electrons to its name from this covalent bond, and hydrogen is satisfied with just having 2 electrons. Chlorine has 2 electrons from the covalent bond plus 6 electrons from these lone pair electrons, giving us 8 electrons in total. So, key thing, bonding electrons shared between atoms counted as belonging to both atoms participating in the covalent bond. Lone pair electrons belong only to the atom containing the lone pair. So, let's now talk about different types of covalent bonds and how we interpret these covalent bonds using Lewis dot structures. So let's talk about single, double, and triple bonds. So bonds are written as lines between each atom. So for example, if we wanted to represent a bond between these fluorine atoms, we'd utilize this single dash. Each line represents one bond or two shared electrons. If we have one pair of bonding electrons, this is known as a single bond. For example, fluorine contains a single bond between these two fluorine atoms. We can represent this as a pair of shared electrons. This example is pretty much identical to our earlier chlorine example. As you can see, this fluorine atom has 2 electrons from the covalent bond and 6 electrons from the lone pair electrons, giving us 8 electrons in total. That is true for both fluorine atoms. Key point here, a single bond is 2 shared electrons. Now, atoms can share more than one pair of electrons and form multiple bonds between atoms to complete their octet. 2 pairs of bonding electrons represents what's known as a double bond. So for example, one way to draw oxygen that we'll see later is somewhat problematic, but this is probably how you drew oxygen when you're approaching it in general chemistry, is where we have a double bond between the oxygen atoms. What this is implying is that there is a pair of electrons shared between oxygen atoms, and then an additional pair of electrons shared between the oxygen atoms, giving 2 pairs of bonding electrons. In other words, we have 4 electrons shared between these oxygen atoms. Now, looking at our count to make sure the octet rule is fulfilled, this oxygen has 4 electrons from the covalent bonds and 4 electrons from its lone pair electrons, giving it 8 electrons in total. Looking at the second oxygen atom, we have 4 electrons from the bonding electrons and 4 electrons from the lone pair electrons on the rightmost oxygen. Again, as you can see, the octet rule is fulfilled. Let's look at this next case, where if we have 3 pairs of bonding electrons, we have what's known as a triple bond. This occurs in molecules such as nitrogen. This can be represented via a set of 3 lines between these 2 nitrogen atoms. We can represent this as well by drawing that triple bond as 3 pairs of bonding electrons. In other words, shared between these nitrogen atoms are 6 bonding electrons. Each of these nitrogen atoms fulfills the octet because we have 2 electrons from the lone pair plus 6 electrons from the triple bond, giving us 8 electrons in total for each nitrogen atom. So, given that we've discussed single, double, and triple bonds, let's apply what we've learned now and let's verify that each atom follows the octet rule in the following structure. So in this case, we have a carbon-oxygen triple bond, and we have our lone pair electrons as so. Now, let's decompose this triple bond into the pairs of shared electrons. And now let's verify that the octet rule is fulfilled. Looking at carbon here, we have 6 electrons from the bonding electrons and 2 electrons from the lone pair, giving us 8 electrons in total. For oxygen, we have 6 electrons from the bonding electrons, 2 electrons from the lone pair, giving us 8 electrons in total. So as we can see, the octet rule has been fulfilled. Okay, let's keep going now, and let's talk about Lewis dot structures. And to this end, let's look at this guide to writing and preparing Lewis dot structures. So for Lewis dot structures, I would encourage you to follow this systematic guide, where we're going to count the number of valence electrons for all atoms. If the species is a cation, you subtract electrons equal to the charge. If it's an anion, you add electrons equal to the charge. We're then going to determine the central atom, which is the least electronegative non-hydrogen atom. From here, you arrange the atoms symmetrically around the central atoms. You form a single bond between the central atom and each surrounding atom, and then subtract 2 electrons from the total number of electrons for each bond made. From here, you can then place lone pairs, electron pairs, representing 2 dots and 2 electrons around the outer atoms until the octet of all atoms is satisfied or you run out of electrons. You need to subtract 2 electrons from your total for each lone pair added. Now, if an octet cannot be fulfilled, you then convert lone pair electrons into a double bond or triple bond until the octet is fulfilled. Okay, this is a lot to take in, but let's show how this systematic process works for some examples. So let's draw a Lewis structure for the following anion. So let's do our electron count, specifically our valence electron count. Oxygen is a 6A element and contributes 6 valence electrons. Carbon is a 4A element, so it contributes 4 valence electrons. And nitrogen is a 5A element, so it contributes 5 electrons. We have a -1 charge, so following our rules, we add electrons equal to the charge. So we're going to put a +1 to our total. Adding this up, we have 11, 12, 16 electrons to work with. We're then going to determine the central atom, which is the least electronegative non-hydrogen atom. Generally, if you have a carbon atom, it's a good idea to put the carbon as the central atom. So we're going to have carbon as our central atom, and we're going to surround it with our 2 other atoms, oxygen and nitrogen. From here, we're going to form a single bond between the central atom and each surrounding atom. So we formed our single bond and we subtract 2 electrons for each bond made. We formed 1, 2 bonds, so we subtract 4 electrons. From here now, we're going to place lone pairs on the outermost atoms first. Given that this oxygen atom currently has 2 electrons to its name and it wants an octet, we're going to add 2, 4, 6 electrons in the form of lone pairs, subtracting 6 electrons from our total, such that this oxygen now has 2, 4, 6, 8 electrons to its name and a complete octet. We're going to repeat this process for nitrogen. Nitrogen has 2 electrons to its name. It wants 8. So we're going to add 2, 4, 6 lone pair electrons. We've used up all of our electrons. We have 0 electrons remaining. Now, although nitrogen and oxygen are incredibly happy with this situation as they have a complete octet, carbon is not. Carbon only has 4 electrons to its name, so we're going to take one of our lone pairs and convert it to a double bond. Unfortunately, we still don't have a complete octet on carbon, so we're going to take another one of our lone pairs and convert it to a double bond. Now, as you can see, nitrogen has 8 electrons, carbon has 8 electrons, and oxygen has 8 electrons. So we've completed and wrote out a valid Lewis structure for the following ion. For those wondering, does it matter which lone pair I convert to a double and triple bond? For right now, no. But later on we'll see that you want to form double or triple bonds in a way that minimizes formal charges. And we'll talk about that momentarily. Okay, let's do another example now, this time looking at a cation. In this case, we're asked to draw the Lewis structure for the CH3NH3 cation. So let's do a valence electron count. In this case, starting with hydrogen as a 1A element, we have one valence electron, and we have 6 hydrogen atoms, giving us 6 valence electrons in total. Nitrogen is a 5A element, contributing 5 electrons, 5 valence electrons, that is. Carbon is a 4A element, so it contributes 4 valence electrons. We have a +1 charge, so we need to subtract 1 electron from our total. This gives us 11, 10, 14 electrons to work with. In terms of these central atoms, each atom can accommodate 4 surrounding atoms, assuming it's not far down in the periodic table, n equals 3 or higher. Carbon and nitrogen, they can only accommodate a maximum of 4 bonds and 4 surrounding atoms. So we're going to make carbon one of our central atoms, and nitrogen is going to be the second central atom. We're going to surround the carbon and nitrogen atoms with up to 4 total atoms. So we're going to put 3 hydrogens each on carbon and nitrogen. This particular formula is known as a condensed formula, so it in fact gives you a hint for the connectivity. 3 hydrogens on carbon, 3 hydrogens on nitrogen. From here, we form 1 bond each between our atoms. 2, 4, 6, 8, 10, 12, 14. We used up all of our electrons, but all of the atoms have a complete octet. Hydrogen has 2 electrons, which is good for hydrogen. Carbon has 2, 4, 6, 8 electrons, and nitrogen has 2, 4, 6, 8 electrons. One finishing touch for the Lewis structures, if it's charged, you put the whole structure in brackets and you put the charge. Okay, so with these examples in mind, let's now try, and I would encourage you to pause the video at this time and attempt to draw the Lewis structure for the following 2 compounds. So I'd encourage you to pause the video at this time and we'll discuss these examples momentarily. Okay, so let's start by looking at the Lewis structure for BH4. So in this case, let's do our valence electron count. Boron is a 3A element, so it contributes 3 valence electrons. Hydrogen is a 1A element, but there are 4 hydrogens, so we have 4 electrons in total. We also have a -1 charge, so in turn we have to add 1 electron to our total. This gives us 8 electrons to work with. Boron is our least electronegative non-hydrogen atom, and we're going to surround boron with our remaining 4 hydrogen atoms. From here, we form 1 bond each, and that uses up 8 electrons from our total, giving us 0 electrons remaining. Boron has a complete octet. Hydrogen has 2 valence electrons. So this structure fulfills the octet and noble gas configuration rules. We put the structure in brackets and put the charge in the upper right-hand corner. Let's take a look at this next example where we're asked to draw the Lewis structure for the following cation. This is a cation that you'll actually see commonly generated in a lot of reactions. This is actually one of the common intermediates generated in the Friedel-Crafts reaction. Nonetheless, when drawing the Lewis structure, we apply the same systematic process. In terms of valence electrons, we see that in this case for carbon, we have 4 valence electrons for carbon. There are 2 carbon atoms, and this gives us 8 valence electrons to work with. For hydrogen, we have one valence electron. There are 3 hydrogen atoms. So we have 3 electrons contributed in total from the hydrogen atoms. Oxygen is a 6A element, which contributes 6 electrons. We have a +1 charge, so we have to subtract 1 electron from our total. This gives us 11, 17, 16 electrons. Generally, you're going to see even electron counts. If you get an odd electron count, that's a sign you're dealing with a radical. And those are not particularly common due to their instability. We will see them, but they're often intermediates. Okay, from here we have to pick our central atoms, which are going to be the 2 carbon atoms. We're going to surround one of the carbon atoms with the 3 hydrogen atoms and the carbon, and the second carbon atom is going to be surrounded with the oxygen atom. Why? Well, the formula is giving us a bit of a hint here as well. From here, we're going to form 1 bond each. 2, 4, 6, 8, 10. That gives us 6 electrons remaining, and I know where those 6 electrons are going to be allocated. They're going to be allocated to oxygen. Oxygen has 2 electrons to its name. It wants 8, so we give it 6 lone pair electrons. This spends our total, and now we see the carbon on the left has a complete octet. The oxygen on the right has a complete octet. The carbon in the middle is very unhappy. It has 4 electrons. It needs 4 more. So we're going to take one of our lone pairs and form a double bond. Carbon is still unhappy. It only has 6 electrons. So to get a complete octet, we convert the second lone pair into a triple bond. This gives us the full complete structure, and we put it in brackets and put the charge in the upper right-hand corner. So these are some examples in terms of drawing Lewis structures. Let's now elaborate upon these examples, and let's talk about expanded octets and formal charge. So formal charge is a critically important idea when drawing reasonable, valid Lewis structures. In terms of formal charge, favorable Lewis structures have atoms with small formal charge values, and they have few atoms with a non-zero formal charge. Ideally, you want your atoms to have as low of formal charge as possible, as close to 0 as possible. Additionally, favorable Lewis structures place negative formal charges on more electronegative atoms and positive formal charges on less electronegative atoms. Now, how do we calculate formal charge? Formal charge is calculated by taking the group number of an atom minus the number of bonds plus the number of lone pair electrons. So in this case, let's assign formal charges to each atom in the following structure. So looking at this molecule here, looking at nitrogen, if we're trying to calculate the formal charge for nitrogen, nitrogen is a group 5 element. There are 4 bonds attached to nitrogen, and there are 0 lone pair electrons on nitrogen. This gives us a formal charge of +1. For hydrogen, we have a group number of 1, we have 1 bond, and a formal charge of 0. So this nitrogen formal charge would be noted with a plus symbol. Let's look at this next case where we have this phosphorus atom. In this case, phosphorus has a group number of 5. We have 2 bonded atoms and 1, 2, 3, 4 lone pair electrons. This gives us a formal charge of -1, and we note that by putting a minus symbol next to the phosphorus atom. I'd like you to take a moment now, and I'd like you to calculate the formal charge of the next 2 atoms using these principles that we've covered. So I'd encourage you to pause the video at this time, and we'll discuss these examples momentarily. So, looking at this next case, calculating the oxygen formal charge. Here, oxygen has a group number of 6. We have 3 bonded atoms, and we have 2 lone pair electrons, giving us an oxygen formal charge of +1. Looking here, we see that this carbon has an assigned plus symbol. Let's prove that. Here, carbon has a group number of 4, and it has 1, 2, 3 bonded atoms. There are 0 lone pair electrons. This gives us a formal charge of +1. Now, why is formal charge important to know? Well, it allows you to draw reasonable Lewis structures, and it also allows us to tackle a specific case, a specific type of Lewis structure, known as an expanded octet Lewis structure. Third row elements and below have empty d orbitals that can be used to form bonds. To minimize formal charges for n equals 3 or greater elements, double and triple bonds can be formed that would lead to an expanded octet structure. Of note, the total charge of the molecule must be equal to the total formal charge of all atoms. So, what does this mean? Why is it important? Well, let's take a look at CH2PH3, which is a pretty interesting reagent. These are used for what are known as Wittig reactions, which we'll see, if not towards the end of this class, in organic chemistry too. So, let's take a look at our electron count as always, and let's draw out a Lewis structure. So in this case, carbon contributes 4 electrons, hydrogen contributes 1 electron, and we have 5 hydrogens for 5 valence electrons total, and phosphorus contributes 5 electrons. This gives us 14 electrons to work with. We're going to designate carbon and phosphorus as our central atoms and surround it with our remaining hydrogens. Again, the formula gives us a key about the connectivity of atoms in our structure. We're then going to form 1 bond each, 2, 4, 6, 8, 10, 12. That gives us 2 electrons remaining, and we're going to place our 2 electrons onto the only atom with an incomplete octet, which would be carbon. Now, does this structure fulfill the octet rule? Yes. Would this be a valid structure in general chemistry? Yes. Can we generate a structure with smaller formal charges using the idea of expanded octets? Certainly so. Looking at the formal charge of carbon, we have a group number of 4 minus 3 bonded atoms plus 2 lone pair electrons. This gives us a formal charge of -1 on carbon. By the same point, phosphorus has a group number of 5, but it only has 4 bonded atoms, so it has a +1 formal charge. To minimize formal charges, we're going to take these bonding electrons and use it to form a double bond. This gives us the following structure. And this structure, even though it has an expanded octet on phosphorus, is much preferred. Why? Looking at the formal charge of carbon, we get a 0 formal charge on carbon and a 0 formal charge on phosphorus. So this is how we can utilize this idea of expanded octets. Phosphorus can form more than 4 bonds, and as such, we can invoke this expanded octet structure to minimize our formal charges. Okay, I'd like you now to pause this video and try to practice drawing the Lewis structure for thionyl chloride, SOCl2, which is a common reagent used in organic chemistry. So take a few moments and try to draw a valid Lewis structure for thionyl chloride, and then we'll discuss this example momentarily. So let's count the valence electrons. For sulfur, we have 6 electrons. Oxygen, we have 6 electrons. Chlorine, we have 7 electrons, and we have 2 chlorine atoms, giving us 14 electrons in total. This gives us 26 electrons to work with. The least electronegative atom is sulfur, so we're going to place sulfur in the center, surrounded by oxygen and 2 chlorines. Generally, the atom capable of accommodating an expanded octet will almost always be your central atom in a lot of these structures. From here, we're going to form 1 bond each. So we subtract out 6 electrons from our total, giving us 20 electrons remaining. From here, we're going to allocate 2, 4, 6 electrons to each chlorine and the oxygen atom to complete their octet. We've used up 18 electrons. We have 2 electrons remaining, and those go on sulfur. Now, everything looks good initially, but as we can see, the formal charge of oxygen is 6 minus 1 plus 6, or minus 1. By the same token, the formal charge of sulfur is 6 minus 3 plus 2, or plus 1. So, just like we did before, to minimize formal charges, we're going to convert one of our lone pairs into a double bond. This eliminates the formal charges. And in turn, if we recalculate our formal charges, we see the formal charge of oxygen is going to be 6 minus 2 plus 4, which gives us 0, while sulfur gives us 6 minus 2 plus, 4 plus 2. 4 bonded atoms, or 4 bonds, and 2 lone pair electrons, giving us a formal charge of 0. So as you can see, we invoke this expanded octet structure in order to minimize formal charges. Okay, so let's continue on now. This is going to be a good stopping point for the first part of today's lecture. We're going to continue on next time with a discussion of valence bond theory and how valence bond theory can be used in order to interpret and describe chemical bonding. So that concludes the first part of the Chapter 1 lecture, and we'll continue on with this lecture in the following video.